Good morning, everybody. We will get started shortly. I'll just leave it a minute or two for any late stragglers to join the session. My name's Adrian Jackson, and I'll be teaching for part of the course today and tomorrow. This what I call single node optimization course, but is also called the performance optimization or optimizing performance optimization on the AMD EPYC processors. Okay, so as I said at the beginning, my name's Adrian Jackson. I'm a part of EPCC here at the University of Edinburgh, and I'm presenting today on the ARCHER2 performance optimization on AMD EPYC processors or single node optimization course. And I'll be giving material today, and my colleague Mark Bull will also be giving some material tomorrow and helping out with practical sessions. And I'd like to thank Claire for doing all the organisation and setting this all up as well. So today and tomorrow we're going to give you an introduction to performance optimization in general. I know the course is very much billed as performance optimization on AMD EPYC processors, and the ARCHER2 services we'll come to talk about is a new Cray HPE supercomputer based on these AMD EPYC Rome processors. But in reality, a lot of the stuff, the majority of the stuff we're talking about here is applicable across a range of processors, particularly across the x86 instruction set processors. So in reality, a lot of the things we're saying now we could have also said for the previous HPC service Archer, which was switched off yesterday, as it happens, and you would be able to take a lot of these techniques to other processors. Now, that's not to say that there aren't specific things you can do to optimize on this specific processor, on this specific HPC system. But in reality, the majority of the things that you may want to do to optimize an application are generic enough that they'll be useful across machines. And this is a good thing, because this means you can do work on ARCHER2 and optimize your code there, but it should also help you on other systems you're working on. But I just wanted to say that up front, that we're not really doing very, very specific optimizations for the AMD Rome processor, other than a few things we'll look at around placement and potentially cache size and those kind of things. But the general performance optimization stuff is applicable to other processors as well. Now, this is a standard training course that we would give with something like ARCHER2, in the sense that I will give a number of lectures, and then there's a set of practical sessions for you to get hands-on with the material we've been teaching. Generally we would give this face-to-face, but of course that's not possible at the moment, so that does make it a little bit more complicated for the practical sessions, in the sense that the people who are teaching the course can't come round and give you a hand and look over your shoulder and check what's going on. So I would say, even more than usual, it's important for you to ask questions if you're having problems, or if something I've said that's unclear, or if something we say is unclear or needs clarification, or you're just not quite sure, is a new thing here, is there something there which could be added to? Could we clarify things? And particularly when we come to practical sessions, it's very much, here's some code, here's an exercise sheet, away you go and have a go with it. But that doesn't mean that you can't come back and say, look, I don't understand what's going on here. Can you let me know? And either by getting in touch and just speaking across this session we're in here, or typing in the chat, or if you're uncomfortable doing either of those, you can send a private message in the chat which no one else can see, or you can even email me. In fact, I should stick my email on these slides so that you've got a place to reference them. And there we go. Hopefully that, I'm going to need to share my screen again. Bear with me. So that you can ask for questions when we if you run into any issues. Now, of course, the nice thing about it being remote is that, of course, you can dip in and out in the sense that you can do the lectures and then you can do the practicals at any time. And as we'll come to see, you've got accounts on the system. You'll have these accounts for longer than we're running the course, so that you can come back and do practicals later or revisit them as well. So that's also fine. But as I say, do ask questions because either it probably, if you have questions, it probably either means that I've not explained things very well, which is likely, or that the practical sheets are not as detailed as they should be, or that there's some problem there. And this is the first time we're running this course on the new ARCHER2 system, so there are bound to be some kinks here in the both in the lecture material and in the exercises that we can iron out over the next 2 days. So really, if things don't make sense, do get in touch and let me know. All the course material that we're giving today is licensed and can be shared. So we're licensing the Creative Commons share and share alike license. I will tell you where all the material is so you can go and get it yourself shortly. But yeah, feel free to use it if it's useful to you. And so ARCHER2 is a partnership funded by EPYC and NERC through UKRI, run and operated by ourselves at EPCC, which is part of the University of Edinburgh, in collaboration with Cray HPE, who provide the hardware. And it's the current UKRI EPYC national service for high performance computing. But just like we had with the ARCHER system before it, it also has a training program and some other things associated with this. And so for the ARCHER2 CAC training program, we are giving 60 days of training a year, free to all academics, and hopefully you know this because you're on this training course. Right, I'm going to switch my video off now, but I did want you to know who I was, so I wasn't just a disembodied voice in the ether. So I don't lose bandwidth completely, I'll switch my video off. And do let me know at any point if you can't hear me properly. Okay, so ARCHER2 has had a little bit of a traumatic birth, in that we should have been up and running with a full ARCHER2 service probably 6 months ago by now, but we're not quite there yet. And this is due to a number of things, including COVID, but also to sort of some issues at the Cray side. When we have the full system up and running, it will be nearly 6,000 nodes, and there's 128 cores per node. So it'll be about 750,000 cores, pretty large system. Each node has 256 gigabytes, although when we have a full service, there'll be a set of nodes which have 512 gigabytes, so some large memory nodes. I can't remember off the top of my head how many of that is. It's something like 300 nodes, I think, but I could be lying. But of that order anyway. So the majority of the system has 256 gigabytes. All the nodes are connected together by Cray's Slingshot interconnect. So that's the Cray new network. And then there will be a bunch of file systems associated with it. So 4 Lustre file systems, each about 4 petabytes, 3 or 4 petabytes, and a burst buffer file system as well. So there'll be a high performance file system for high performance storage, even faster than the Lustre file systems. At the moment, we're on a reduced service until the ARCHER system, which was switched off yesterday, has been taken away, and the new ARCHER2 full system has been brought in and built and deployed. And when that actually happens is still being decided. It's still being worked through, but sort of by summertime, we would hope that the full 23 cabinet 5,800 node system would be up in place. At the moment, and the system you're going to be using today and tomorrow, or maybe already have been using, because I know some of you are ARCHER2 users already, it's a 4 cabinet system, which is 1,024 nodes. Still quite big. It's still, 130,000 cores, but small compared to a full system. We only have one of those file systems. We have no large memory nodes, and we have no burst buffer file system. But other than that, it's exactly the same as the full system would be, just smaller. Okay, so that's ARCHER2 in a nutshell. Now, of course, we're going to go into much more details on the hardware itself over the course of today and tomorrow. That's the purpose of this course, is to try and give you some insights into how to optimize applications on that hardware. But before we get going, just a little bit of background on who we are at EPCC and the training program in general, and then we will kick off in earnest. So EPCC is a supercomputing centre at University of Edinburgh, and we've been heavily involved in running and operating these high performance computing services, including the previous one, Archer, but all the way back to something called the Cray T3D in 1994. And we also do research and commercial products, and we run a master's program in high performance computing and high performance computing in data analytics. In terms of the ARCHER2 program, you can see that we have a set of training courses, which this is one of, so you should be aware of them. And the nice thing about those is that the material from them is freely available online. So you can go and have a look at the sort of past courses, the virtual tutorials we do, and the documentation on the system. And the documentation is a good place to start for a lot of your questions on ARCHER2. My name's Adrian Jackson. I'm a research fellow at EPCC, and so as well as doing things like this, teaching and supporting users on HPC systems, I also do research into sort of parallel computing, parallel programming models, and novel computing hardware, in case you were interested. We should ask, we like to point out up front that it's very important for us to get feedback on the training always, but especially now, given this is a first run of a course on a new service. It's going to be important for us to understand what works well and what doesn't work. So there is a feedback link for you to give feedback on the training, which is online. I don't know if it's active yet. I'll check in a second. But by the end of the course, once we're finished tomorrow, if you could give us some feedback, that would be great. It doesn't have to be anything earth-shattering. In fact, I think the first page is just, was it good or was it bad? And then you can give more detailed feedback if that's useful. But I'll remind you again about that tomorrow. And then in more general help, if your general queries about, and that should say ARCHER2, not Archer, there's a full help desk which can support this kind of thing. So you can just email support@archer2.ac.uk. I'm quite happy to take questions today and tomorrow or for the next few weeks, given you have my email address about ARCHER2, but in general, there is a full help desk for supporting users on the Archer service. Now, for ARCHER2, we've moved to a new model of providing you access to the system for the training courses. What we used to do in the past was give you guest accounts, so a sort of generic accounts which would be used between courses, and you were given a guest account on the day and a guest password, which was the same for all the accounts, and away you went. And now what we do is we set up a project for a course, and you sign up and get your own account, your own personal account. You choose the username, you get your own password, and that becomes yours on the system. Hopefully you're all aware of this, because you should all have accounts in this project called TA013. And the only reason that's interesting to know is because that's also the account for charging when we're submitting jobs to a system, and we some of the back scripts for the exercises will say, what's the account number, and it's TA013. The nice thing about this model is what we used to do is you had these guest accounts, and they at the end of the course, the guest accounts are closed and you lost access to a system. Now we can keep these projects open for longer, and in general, these course accounts will be not active forever, but should be active for up to a month after the course is finished, and you have a little bit of time in them to run jobs on the system. Having said that, I know some of you already have your own ARCHER2 accounts, and you can use those for the course rather than using one of these project accounts for the course, one of these TA013 accounts. The only caveat is that we have set up a reservation on the system with a bunch of nodes dedicated for the course, and that's only accessible through this TA013 project. Now that reservation means that your jobs you submit get through the queue quicker, and you have a quicker turnaround. You don't have to wait for them to run. Having said all that, at the moment the system is not hugely oversubscribed, and there is a debug queue you can use. So if you want to use your own account rather than the one from this project for this course, feel free to do so. And if your jobs are taking a while to run, let me know and I can tell you how to run on the debug queue, which is a similar reservation, which is generally not busy at the moment. So that should work for you as well. Having said all that, these accounts will be closed 2 weeks after access ends, so that would be in a month and 2 weeks. So it would be useful, if you're wanting to retain that data files from the accounts, then to copy that off by the end of the access period, otherwise you'll lose it. Yes, okay. And the course material for this this course is available from the ARCHER2 website, and in fact I'll point you to where it is shortly. We do have a code of conduct for trainees on both trainees and trainers on the ARCHER2 courses, so it's worth having a look at that. Now, it generally outlines the behaviour that's expected of people on the courses. So if you have any issues associated with that, or with anything like that on the course, please do let me know, or have a look at the code of conduct and have a look for the incident reporting form. And finally, for the ARCHER2 service, it's always worth us pointing out that ARCHER2 comes with the system and support and the training program, but it also comes with this thing called ECSC, which stands for Embedded Computational Science and Engineering Support. And this is a funding program which lets you ask for time, either for somebody to work on your code, or to get money to fund somebody locally at your institution to work on your code, to do one of the things listed here in this scope of funding. So algorithmic improvements, scalability improvements, sustainability and maintainability improvements, porting or bringing new codes to ARCHER2. So effectively, it's quite a nice way to fund work which is often hard to get funded through the research councils, in that it's designed to support implementation work on applications. So I want to make this code go faster. I want to add a new bit of functionality into this code, and you can, I think, have up to 12 months of effort to do that. So there are regular calls for this, I think 3 times a year, but this web page here has more details on that if you're interested, and there's a call open at the moment for ECSC stuff. The other, so this course is an ARCHER2 course. It's also what's called a PRACE course. And PRACE is the European Partnership for Advanced Computing in Europe, which brings together all the European countries and aims to provide both access to computational hardware across Europe. So just like ARCHER2 is a service in the UK for UK academics, PRACE is a service across Europe for European academics to get access to systems. And we are still part of that, even though Brexit has happened. And ARCHER2 is a service in this. So it's a quite a nice project in that you can bid for large amounts of compute time on systems around Europe and get it just in the same way you can bid for time on ARCHER2 for your research. But it includes a wider range of systems, a bit like the tier 2 systems in the UK. So the UK tier 2 systems provide a more wide range sort of computational landscape with different bits of computational hardware in there. And this program also has a set of training centres, of which EPCC is one, but there are other ones around. So if you want to have a look to see what kind of training courses they have, then this trace www.training.prace-ri.eu is a great place to go and have a look at. Okay, so I'm already wildly over time here, but this is the kind of timetable we're looking to follow for today, where we'll have this introduction, and then I'm going to talk about node architectures. So the hardware in Archer, so it's lectures, and then it'll be slightly after 10:30 now. We'll get our first practical on the system, then we'll have a break, and then there's a lecture on profiling, a practical on profiling, and then we'll take a lunch break 1 till 2, come back and have a lecture 2 till 3, and then after that it's practical all afternoon. But we'll have a brief summary at the end here. So these are very much give you a lecture and then you go and have a look at the practicals. And as I say, in this context, if you know it's not as easy for us to support you remotely, so these are the times when it's great if you can come and ask us questions or tell us what's going wrong or ask for help. And we'll try and stick to this timetable reasonably well, although as you've already noticed, I'll probably go over time on the lectures. And then tomorrow morning there's a session given by my colleague Mark Bull on OpenMP optimization, and a practical associated with that. And then tomorrow afternoon we look at some more in-depth topics in vectorization and memory optimization, and then practicals after that till the end of the session. Now, as I've already mentioned, because we're doing this remotely, and because you have access to these systems, the system for longer than these 2 days, then you can take the practicals and do them in your own time if you'd rather, or come back and revisit them. But we will be around, myself and Mark will be around during these practical sessions to give you that consultancy if you're looking to do them now. And it is useful to do them once we've taught the lecture on them, because it's all fresh in your head and you can go and have a look at that. The lecture notes and the practical handouts are at this GitHub page here. Now, this should also be linked off the ARCHER2 training page for this course. But if you go onto this page here, you should be able to find the lectures that we're giving throughout the course as PDFs, and then also the exercise stuff. Now, the exercise stuff is not quite there yet. I need to push it from my laptop here up to the repository, which I'll do after the next lecture. But everything else should be pretty much there. But if there's stuff that's not coming up correctly or stuff you're having problems with, then do let me know, please. And when we come on to it, what we'll also do is the source code for the practicals is on the ARCHER2 system. Now, again, I need to push it from my laptop to there to make sure it's updated, and we've got the latest version. So don't do this yet. But when we come to it, the source code we're going to use in the practicals, you can copy from the file system on ARCHER2 like this. Yep, I will put the link to the course materials in the chat. Give me a second. But yes, also, we hope that you enjoy the course, both informative and enjoyable, we're hoping. But as I say, do let us know if you have any questions. Thanks for putting that in there. Yeah. So the way we've set up these, thanks everybody for putting up the links. The way we've set up these practical repository is because the course may change every time we run it slightly. I want to be able to have a repository of the materials as it was when you sat the course. So we create a new version and a branch every time we run it, and so that the main repository for this course is empty, but each branch will contain the actual slides and the exercises. So this one we're running today is under this tree 2021-01-29 branch, so that so it can stay there in perpetuity. Any other questions before we get going? If you'd like me to slow down whilst I'm speaking or change my microphone or anything like that, also do let me know. Okay, so this is a course designed to talk about optimizing applications on ARCHER2 nodes on the AMD EPYC Rome processor. So what we want to do really is have a look at what the node architectures for this system and in general looks like, and then what will follow from that is how we can optimize applications from that. Now, I just lost my screen slightly. There we go. Okay. Now, HPC systems, like any other computational system, have a set of things associated with them. So the computational nodes in HPC systems aren't that different to your laptop or in reality to your phone. Computers need a certain set of things to operate. And so we have a set of technologies here which are important to us because they're vital for your application to run, and that they're also vital to get good performance out of your application. And broadly speaking, we're looking at processors which do the processing, do the calculations. They require memory for storage of data. We need an interconnect, particularly for our HPC systems. We need an interconnect to be able to use multiple processors together to get our parallel applications working. And we also need storage for long-term data, so not temporary storage, but long-term storage. So, this is generically what you need for computers. In general, of course, you can run a computer without an interconnect, but in reality, all the computing we do nowadays is generally on connected systems. And all of these places in the technology hierarchy have scope for performance impacts on your applications or performance optimization that can be done. Because this is a single node optimization course, what we're actually most focused on here today are the processors and the memory side of things. And we're not really going to look at optimizing on the network. So there's a whole bunch of things you can do to make your application faster, parallel application faster using MPI or using other messaging layers and using things for using things to optimize the network. And there's a whole bunch of things that you can do to get better performance on file systems, on the Lustre file system or on the burst buffer that ARCHER2 will get, and how you write data out to files and how you read data in from files. But we're not really going to focus on those today and tomorrow. We're focusing on stuff that's applicable inside a single node for an application, so processors and memory. Now, in reality, there's a lot of things that we can have a look at here now. So it could be a very large topic, performance optimization on processors and performance optimization on memory. But we're going to go and have a look through the basic building blocks for processors and the basic building blocks for memory, because these are the things which have performance impacts for applications. So what does a processor do? In general, it has basic functionality where what you're looking to do is execute instructions to perform arithmetic operations, either integer operations or floating point operations, and floating point ones tend to be particularly important for computational simulation, which we see on systems like ARCHER2. Quite often, for other applications in other domains, then integer operations are more important. If you are writing applications for machine learning, then some combination of the two may be important as well. But in general, for computational simulations and the kind of things that at the moment get run on ARCHER2, floating point performance tends to be dominant. But of course, processors also do things like loading data from memory and storing data to memory. There's no point doing operations without data. And then there's a whole set of functionality to schedule and execute instructions. So you have a stream of instructions which makes up a program, deciding what instruction to run where, what data you need for each instruction, and what data each instruction generates is what the processor does. The processor works on data which is stored in a local memory called registers, and that data that's in registers needs to be fetched and stored using these load store operations, where the processor explicitly asks for data to be loaded and explicitly moves data off in a store. Now, processors have separate registers for integer and floating point, and indeed separate registers for integer, floating point, and vector operations. And it varies how many registers the processor has, varies from processor to processor, but you're looking at, order of 100 registers for integer and 100 registers for floating point operations. And this can have a performance impact. The number of registers you have can have a performance impact on your application, because as we'll come to see, processors can have many instructions going on at any one time, but of course are limited by the amount of local storage we have to maintain temporary data and maintain loaded and calculated data before they stop being able to run new instructions. Processors vary a lot depending on their instruction set and their particular design, but they also have some sort of basic characteristics which are important, including their clock speed, so how many instructions they can execute per second, and modern processors 2 or 3 gigahertz would be a sensible clock speed or a normal clock speed. And also the peak floating point capability, because as I've already said, for computational simulation, floating point performance tends to be very important. Their peak floating point capability is also important for the performance you can get from them. And now if you went back far enough, if you went back 20, 30 years, the peak floating point capability would be the same as the clock speed. If you had a clock speed of 2 gigahertz, then you could do 2 gigaflops of floating point operations. So you could do a floating point operation per cycle, and you can do that many cycles, so you can get that many floating point operations. Since then, the performance has diverged from the clock speed because processors have extra functionality in them to do more floating point instructions per clock cycle than a single floating point add or multiply or operation like that, particularly around vector operations. So modern processors have vector units in them, which let them do multiple floating point operations per clock cycle. And we have a whole lecture on vector units tomorrow, which we can get into more detail on there. But there are other optimizations as well. So fuse multiply adds or superscalar vector units where you can either do a multiply and add in a single clock cycle and that doubles your floating point performance, or you can run multiple floating point units at the same time. Yeah, okay. So as we've said, clock speed will determine the rate at which instructions are executed. And in fact, I've just said all this. But modern processors are what we call superscalar. And that means that you can run multiple things at once because there are multiple functional units inside a processor. So a processor, and when we say processor here, now I'm talking about a core, a compute core inside the processor. But a processor here, we can think of as a monolith, but in reality, it has a number of different functional units inside it, where it has a floating point unit and an integer unit and a load store unit and a branch prediction unit and maybe other things in there. And modern processors are superscalar in the sense that they can use all of those at once. So every clock cycle, it can theoretically do something on every one of those things at one time. So you can run an integer instruction and a floating point instruction and a load store in the same clock cycle. And so we have this ability to, if our code is structured in the right way and efficiently using all parts of a processor to do more things per clock cycle than you would expect. And then underlying all of that, there are a whole series of hardware innovations and hardware changes that have happened to processors over the past 30 or 40 years, which have aimed to speed up performance for applications from pipelining. So this lets you have functional units which take more than one clock cycle to complete, but still produce an instruction per clock cycles because you can have a pipeline of instructions that are running through the functional unit, doing parts of it, and once you've filled that pipeline up with instructions, it will generate an instruction per clock cycle, through to out of order execution and speculative computation to allow a program, a set of instructions to be efficiently scheduled on the hardware, so you don't have to take it in the order the programmer defined, but rearrange instructions. The processor can rearrange instructions to best use the resources it has up to a limit. Or the processor can speculatively execute instructions even if it's not quite sure that they're going to happen yet. And this is, of course, all to do with branches in codes. If you have if statements in a code, or if you have a loop, the processor won't actually know which instruction to execute next until that instruction is finished. But of course, if you have a pipeline of instructions that are being worked on, if you have to wait for that instruction, the branch instruction, to be completed, then you effectively have to drain down your pipeline to get the branch instruction result, and then start filling your pipeline back up again. And this impacts performance. So there's a whole set of functionality inside processors to try and predict what branches what will happen to a branch. And a branch in this case could be an if statement in your code, but it could also be a loop. So loops are effectively branches as well, because at the end of a loop, each time you check, do I need to continue, yes or no, and then continue around the loop. And so, but as computational simulation codes tend to be large loops across floating point numbers to do operations, if you had to drain down that pipeline every time you got to the end of a loop, you would end up reducing the performance you get out of the processor. But modern processors do a good job of predicting what's going to happen and speculatively executing instructions, and then checking what did happen. And if it made the wrong prediction, it rolls back the instructions and negates the changes. But of course, to do that, it needs to have good prediction, and it also needs to be able to have enough temporary storage on the processor in these registers to be able to keep track of these results that it may have to roll back. So it has to sort of keep copies of data that's been changed, so that it can restore it. And interestingly, this speculative computation functionality was the cause of the Spectre meltdown bug, which was identified a couple of years ago, where speculative execution could actually end up leaking sensitive data to users if used incorrectly. And the fix to that was, of course, to disable the speculative execution, but that impacts performance of applications. And we've seen issues with the hardware here as well. Okay, so computers have all this complexity here. So these processors have all this complexity here: pipelining, out-of-order execution, superscalar, instruction issues, speculative computation, all sorts of things going on in them. This is partly because over the past 40 years, Moore's law has meant that we've been able to pack more and more functionality into processors. So Moore's law, or Moore's observation, was really that the number of transistors that you could put in a processor doubled every 18 months to 2 years. And for a while, that meant that CPU power doubled every 18 months to 2 years. But of course, we got to the limit where you could actually push the processor faster by adding more transistors into it, for a number of reasons. Partly because the way that you push processors faster generally is to increase the clock speed. To increase the clock speed, you increase the power that goes into the processor. And then there's only so much power you can put into a processor before it sets on fire. So to reduce the amount of power you're using, you have to reduce the voltage used on the transistors, because power equals clock speed, or frequency times voltage to some degree. And the transistor manufacturers are, and the processor manufacturers have got to a point where this reduction is not in voltage is not really possible anymore. So we've got to a point where it's hard to reduce the voltage used in a transistor on the processor anymore, because the transistor just doesn't then recognize the transition between a 1 and a 0. But the amount of transistors that manufacturers have been able to pack onto processors, onto silicon wafers, has still gone up. And that means that what we've been doing, what processor manufacturers have been doing over the past 10, 15 years, is to look at improving performance of a processor by either looking at these pipelining, superscalar, these kind of things, using the transistors to add extra functionality to a processor. And that has helped, but we're reaching limits with that as well. And then actually putting more processors on an individual chip. So that's what we've seen happen over the past 15 years, is this move to multi-core processors. Because we've got all these transistors, we can put them onto a single processor, but we can't make an individual core go faster. Let's add more cores onto the chip, so overall the whole processor is faster, even though the individual processing cores may be slower than they were in the past. And so that's where we are now. The ARCHER2 system, as I've already mentioned, each node has 2 processors. Each processor has 64 cores, so we have 128 cores in total. If you compare that to the system that was just decommissioned, Archer, it had 2 processors per node, the same. Each processor had 12 cores, and we had 24 cores overall. So in the past 7-8 years since the processor for Archer was manufactured, and now we're on Archer2, you've seen a sort of 5-fold increase in the number of cores per processor, to give more powerful computers and use those extra transistors that processor and silicon manufacturers have been able to come up with. Now, of course, this has impacts for us because the individual cores have not got 5 times faster. If you compared an Archer to an ARCHER2 core, it would not be 5 times faster, but the overall processor has got faster, and we've got more cores. So we could probably look at seeing, you know, chip-to-chip comparisons of about 4 times faster between the systems, but the individual cores themselves haven't got that much faster. That means that we are pushed much more towards doing parallel programming to get our applications good performance on these systems. Now, this shouldn't be a surprise for anybody using ARCHER2. It's a large-scale parallel system, so you know parallel programming is the way to go. But it does mean that parallel programming is increasingly important across all areas of computing these days. Okay, I am wittering on here, so if you do have any questions about anything I say, I'm not stopping, but please do interrupt either in the chat or just speak to me. I'm more than happy to take questions and clarify anything I'm saying. Okay, so the processor itself has a number of functional units, as I've already said. They vary across processor designs, but in general, what you'll have is an instruction unit. So this is responsible for fetching, decoding, and dispatching of instructions. And so there's a separate instruction cache. So the instructions here are your program. Your program is compiled down into a set of machine instructions. And then when you run it, those instructions are loaded onto the processor and tell the processor what to do. And for our x86 instruction set, which AMD and Intel processors are, there's a set of functionality where the instruction is fetched from a cache, then decoded, and then that tells the processor what to run next. And the processor goes through its cycle every clock cycle. In terms of actual work for your application, there'll be integer units which handle integer arithmetic, addition, multiplication, and division, also logical operations. The integer unit can also be known as the ALU. Now, I should say that both for floating point and for integer, division is expensive compared to addition and multiplication. So division can easily take a few more clock cycles than an addition or a multiplication can. And the floating point unit, or one or more floating point units, and you know, high performance processors nowadays may have multiple floating point units. If we had a look at the Fujitsu A64FX processor, it has 2 floating point units per core to give its high performance operation for computational simulation. And so the floating point unit or units handle floating point addition, multiplication, division operations, these kind of things. And it's, you know, critical for performance for computational simulation, as I've said. The floating point units and what they can do will, you know, define what the peak floating point performance of your system is. And this tends to be a number which is used to sort of sell and also evaluate large-scale high-performance computing systems. Of the top 500 list of, which is the list of the top 500 fastest computers in the world, is evaluated on this sort of floating point performance numbers. There's a control unit which will do branch prediction and handling where the code goes next from branches and jumps. There'll be a load store unit for taking data in from memory and storing it back to memory, and then your registers, so the local storage associated with your processor, your core, and your application as it's running. There may also be a whole bunch of other things on the processor: memory management, cache controller, bus interfaces, graphics things. In reality, for modern multi-core processors, a lot of this extra stuff at the bottom here is shared between cores, is not dedicated to individual cores. So each core will have generally have its own integer and floating point units, own control units, and logical load store units and register files. But then we'll probably share some cache controllers, memory buses, and these kind of things. Now, as I've already mentioned, pipelining is important. Is an important performance feature for modern processors. So execution of instruction inside a unit, a functional unit, is generally broken down to stages, and then each stage takes a clock cycle, and you can then have multiple instructions running through this functional unit at once, which means that we can have multiple instructions in flight and still be producing one instruction per second. So this allows one instruction to be completed per clock cycle, even though the instruction itself may take many cycles to complete. This also lets us pipeline loads, then arithmetic operations, and then stores. So we can do your load operation, followed, and then pass the data straight into the arithmetic units, and then pass that data straight into the storage units, and keep our processor busy that way. The AMD EPYC Rome, so the processor we have in ARCHER2, has a 19-stage pipeline. So we have to be filling up the processor with large numbers of instructions before we get to this point where we have these one instruction being completed per clock cycle. And so you can see from this, if your application changes what it's doing frequently, then you may have reduced performance because your pipelines are not always full. But of course, for computational simulation, generally we're in this good position where the main computational kernels are small and compact, and iterate over large data structures, so we can keep our pipelines full. Not all instructions are pipelined, though. Things like floating point square roots and floating point divisions may not be pipelined, and so these can be expensive operations for your application. And this is one of the reasons why compilers, if you let them, will try and get rid of some of these operations and replace them with other things. So you can take a divide and turn it into a multiplication by a reciprocal, and do some common sub-expression replacement to try and get rid of divides across your application. Now your compiler may be able to do this for you, but of course this potentially changes the results you get, because floating point arithmetic is not has a fixed precision, and so the order you do things in and the operations you undertake may impact the results you get. And so a lot of the compilers won't do some of these things by default, because they can change your results, change your maths, and so you may have to enable them. And we'll have a look at compiler-based optimization later on today. So pipelines can stop, there are a number of what we call pipeline hazards, which can waste cycles and give you performance reductions for a given code and a given piece of a given processor. And these can be things like instructions which aren't pipelines, at a floating point division potentially, or square root, but also things like two instructions requiring the same hardware resource at the same time, one instruction depending on the result of another one, or the one instruction depending on a branch. And some of these are optimized away for us by the processor by some of the functionality we have. So this outer order of execution, where the processor itself can reorder instructions that are given to it from the program to make best use of resources. So that will try and get rid of this two instructions requiring the same hardware resource at the same time. The processor will try and schedule the instructions it's got in such a way as to avoid this. It can't always do that, but we will try and do that. And then the branch prediction hardware will try and guess where the branches go, and that will try and get around this result of instruction changes hazard to the pipeline as well. And so the hardware is working under the hood to try and do these things for you. And there are times when you can see the performance of applications reduced because this isn't working for a number of reasons. One of them might be you genuinely have these dependencies and the branch prediction's not working well, or you have to wait for the result of an instruction to complete before you can get the result, and there's nothing else you can run until you get that result. No other instructions that can be executed. Or it could be you're running out of registers, so the processor could do optimizations, but it's running out of temporary storage. And you know, there are things you can then do to optimize your application to remove some of these bottlenecks, and we'll look at those later today and tomorrow. Yeah, so pipelining is this form of instruction level parallelism where we have multiple instructions in flight on the processor at any one time, and on the AMD processor we're using for ARCHER2, this will be up to 19 instructions per clock cycle will be being executed. But you can also use multiple functional units at once, what we call supercalar processors. So we can have 19 instructions in flight, but we can also use multiple functional units at the same time. And we can use vector hardware in the floating point and the integer units to run multiple instructions in a single clock cycle as well. So there are these other ways we can do parallel computing to give, inside the processor, to give good performance for applications. Now, again, this is not you explicitly, generally, this is not you explicitly doing this as parallel computing, but it's ways the compiler will take your application and then turn it into something which can run in parallel on the hardware it knows you're compiling for. So it will try and schedule multiple of these functional units at once, and it will try and make sure that your application code is mapped to these vector instructions so that it can give you good performance on the processor. Now, you can do manually some of these things in your code, but that tends not to be very portable. So what's important is generally, and we'll come on to see this, structuring your code in such a way that the compiler can do this automatically for you. And then that way, you should be able to get the same kind of performance across a range of processors, rather than having to write something which is specific to an individual processor or an individual instruction set. Yeah, so supercalar processors is generally done and supercalar processing is generally done in hardware with multiple instructions scheduled at once, but they need to take into account the structural and data hazards. A structural hazard being two instructions require the same hardware resource at the same time, and a data hazard being one instruction depends on the result of another instruction further down the pipeline. And the compiler the compiler will try and do this, and then the hardware will try and do this once it's got the instructions there. So the compiler will try and do this by grouping together instructions in ways that favor multiple issues, and then the hardware will pick instructions at runtime to try and do this as well. So the supercalar stuff, there are little bits and pieces you can do with your application to try and make it amenable to supercalar processing, i.e. multiple instructions being able to run at the same time. But in general, there's not that much you can do. The compiler will do a good job of what it can do, and the hardware will do a good job of what it can do. But you tend to be restricted to the actual application composition that you have. So you can do things like merge loops, which are doing different operations. One loop's doing floating point operations and the other's doing integer operations. And if you merge them together, then you get this mix of floating point or integer operations. and that can give you this kind of performance benefit. But most applications aren't like that. Most applications, you don't have these sort of separate loops doing different types of instructions. And so in general, the compiler and the hardware will try and work this out as best as possible. There's not huge amounts you can do to it yourself. Likewise, we have these SIMD instructions, so vectorization, and we have a whole lecture on this tomorrow. We don't have to worry about this too much, but this is the idea that we can do multiple of the same operations on different bits of hardware in this, different bits of data in the same instruction. And so modern processors will have these. We're looking at an AVX2 or an AVX256 instruction set in the AMD Rome processors, and they let you do, depending on the size of your data, something like 4 or 8 bits of data at once in a single instruction. And now this requires extra, special hardware in the processor to do this, so multiple arithmetic units and multiple register vector registers to store this data, but it can give you 4 times the performance than if you didn't have it in there for not that much more transistor required on the processor. So it tends to be beneficial for high performance computing. Again, this is the kind of thing we would like the compiler to do for us. We don't want to have to write vector instructions direct in our code ourselves, because these tend to be processor specific, and then that reduces your portability across systems. But there are a bunch of things we can do to help the compiler identify when we can vectorize an application, because the compiler quite often is conservative and it wants to maintain correctness of the program. So often it's not doing the vectorization because it thinks there are some problems with the code to vectorize, but you can fix that by either changing your code or reassuring the compiler that the vectorization is fine. And one of the key things is data alignment and making sure data is aligned on cache boundaries. But as I said, we're going to talk more about this in detail tomorrow. Then this sort of wider set of coarse-grained parallelism. So I don't know if you remember a few slides ago, I was discussing, there are different ways that processor manufacturers have aimed to use these extra transistors that they have access to give better performance on applications. And we've had the fine-grained parallelism approach of superscalar processors and vector units. But with more coarse-grained parallelism, where we have multi-core chips, like we have on ARCHER2, we have generally completely separate cores, where they have their own functional units, and they have their own caches as well. And we've not talked very much about caches yet, but we have our own caches as well up to some point, but also share some parts of a processor as well. So they'll generally share a level 3 cache between cores, and then generally share memory bus and memory accesses between cores, and interfaces to other processors between cores. They may share functional units. So AMD's Bulldozer processor from about 10 years ago, every 2 cores had one floating point unit. Each core could use it, and it could be shared between them as well. So that is also possible. So modern processors look like this, where we have a single processor, where each processor has its own L1 data and instruction cache. Each processor probably has its own L2 cache, or it may be a shared L3 cache across a chip, or L2 cache across a chip, and there may be a shared L3 cache between a processor, and definitely they'll be sharing access to main memory as well. And so these sort of features can be important for program performance as well. The size of these caches and how they're shared can impact the performance you get on applications. The nice thing about this is that because we have so many processing units on the same processor, 64 on ARCHER2 per processor, we actually have a way of communicating between them at a high bandwidth, low latency through its shared cache. And so for some applications, either if you're doing parallel processing with MPI or OpenMP, you may be able to, if you structure your program correctly, get performance benefits for sending data between the workers through this cache level, rather than having to go out to some kind of network card or going out to main memory. But of course, there's also a downside to this shared resource of cache, in that cores are now contending with each other for space in the shared cache. So you may also suffer, if your application is using the data and memory in a certain pattern, you may suffer performance reductions through this cache sharing because of the way the modern hardware works. And you're also sharing this off-chip memory bandwidth as well. So there's also competition between the cores for access to main memory. As we'll come on to see, it does mean that individual core, if you're running nothing else on the processor, just running one program on a single core, you may have access to more memory bandwidth than you would if you were running 64 things per processor, because other things will be contending for memory bandwidth as well. And so we can see different performance for applications if we fill up the processor or if we underpopulate, i.e. we run less programs and we have actual cores available. And for some applications, you may get performance benefits doing that because you have access to the memory bandwidth per core that you wouldn't normally have. Now, I've started talking here about memory and cores and really not motivated it very much. But there's a sort of a slide missing from this discussion here, which is the slide which says that memory and processor performance has diverged over the past 30 years. So if you went back 40 years, actually the processor calculated instructions was slower than your memory. So you could fetch data to work on in the processor at effectively zero cost for your application, because it took you longer to process that data than it did to fetch it from memory. Now that performance differential has not lasted, and actually processor speed has got much faster than memory speed, and that means that nowadays it will take you thousands of clock cycles on a processor to fetch data from main memory. And this is one of the main performance bottlenecks for most applications using a system like ARCHER2. They tend to be memory bandwidth bound in the sense that they are always performance bound by how quickly you can get data from memory into a processor and back out again. And one of the big things you can do to optimize your application is make sure that you use these fast, small memory spaces, these caches, which are on the processor, designed to get around this performance bottleneck. Make sure you can use those efficiently. And so this is what the caches are here for. Now, there's another byproduct of this on-processor parallelism functionality that we have on-core parallelism, in that because modern processors are superscalar, they can generally run multiple things per clock cycle, use all the functional units per clock cycle. But actually, most applications, as we've already discussed, aren't generally amenable to running loads of things per clock cycle. So, a typical superscalar processor can run 4 or 5 instructions per clock cycle, going to different functional units. But a typical application, if you have a look at it, doesn't have that much in parallelism. So it might have 1 or 2 instructions that it can run per clock cycle. And this often means that for processors, some functional units are waiting, doing nothing in a clock cycle, because the application that's been run, the program that's been run, isn't able to fill up or doesn't require those functional units all the time. This has spawned the trend for extra hardware in processors to use these spare functional units for other things. So to give performance improvements to the processor by keeping it full all the time, people have said, actually, why don't we run multiple programs on the processor at the same time, not just one program, multiple programs per core. And if one program is not using all the functional units, then another program can use the functional units it's not using. And this is what we call hyperthreading, or sometimes simultaneous multi-threading, SMT. And this is the idea that if you add a little bit of hardware, extra hardware into a processor, so something to keep track of instruction pointers and TLB misses and registers, then you can run more than one program at once on a given individual core, because each program will be using different functional units. And this theoretically means that you get twice the throughput of applications on your processor, because you can run twice as many things at once, or 4 times as many things at once. So here's a simple graphical example of doing that. Here we've got 2 cores and 2 programs are running on those cores, the red program and the blue program, and each column of these is a functional unit. So you could say that's the floating point unit, and that's the integer unit, and that's the branch prediction unit and the load store unit and a control unit, and the same here, floating point, integer, branch prediction, load store and control units. And then each row here is a clock cycle. So this is first clock cycle and second clock cycle and third clock cycle and fourth clock cycle. And if we look at these 2 programs, we can see that each clock cycle they're using different functional units. So they're using the integer and the branch prediction unit, and then the floating point and the load store and the control unit, and then the integer unit again. But at each clock cycle for both programs, they're leaving some of these functional units empty. So they're not using all 5, they're using at most 3. And so the idea here is, instead of running these on 2 separate cores, can we put them together and get them and schedule the instructions in such a way that they use separate functional units when they're running, and get a more full processor and get our programs through quicker. And so this example here, which we've just made up, I mean, it's not a real example, but this example here, if you put them together, you can see actually now, instead of at most using 3 functional units, we're actually using 3 or 4 functional units most clock cycles. And the way these programs are structured, you can put them together so that you can run both programs and not both programs in the same time, but you only need 1 extra instruction to run both programs. So we're getting an almost 50% speed up to get those 2 programs through the processor. Now, of course, you can't run them exactly the same way, because there are points where they're looking for the same functional units of the same clock cycle. So you can see here at clock cycle 2, they both want this load store unit. And so to fit that in on the processor, we have to bump one of them onto the next clock cycle. And that needs extra logic in the processor, and you need to keep track of extra data and these kind of things. But theoretically, you can see here this idea of hyperthreading or symmetric multi-threading, which is commonplace in modern processors, gives us really quite a nice performance improvement for the processor, not for each application. Each application actually really either takes the same time or slightly longer, but for one core, we can get twice as much work done, really. So this is the idea behind hyperthreading or SMT. In reality, particularly in computational simulation, because we spend most of our time in applications using the floating point units, there actually isn't that much overlap you can do for a lot of scientific simulation applications. So here you can see you've got nearly 50% overlap you can nearly sort of half the runtime of the two combined programs. But for computational simulation applications, generally you might only see a sort of 10, 20, 30% performance improvement for this symmetric multi-threading or hyper-threading. And actually for some applications it can make your code go slower because you're running twice as many things on the processor. You've got twice as many things competing for cache space and for memory bandwidth and for these kind of things. So it can be a performance benefit for applications, but it can also be a performance degrader. Now, the nice thing about hyper-threading or symmetric multi-threading is you don't have to change your application to use it. You don't have to change your code. You just have to switch something on or off on the processor, and so you can play around, do it yourselves, and not have to do any extra work. And ARCHER2, the processors have this hyper-threading enabled, so you can run two things at once if you want. But by default, the way we run jobs, you don't get it automatically, and then you can run a job in a slightly different way and you will get it. So it's one of the interesting places to try first of all to optimize an application is to see if hyper-threading is beneficial for your application, because if it is, then you can not get your results faster, but you can use half the amount of resources you were using before, because you can fit twice as much on per node, and that can be very beneficial to you in terms of efficient use of resources that you have. And so you can just try that out on the system and see what it does. Of course, there are other ways of optimizing computer applications by using extra hardware, and one of them is accelerators. So GPUs would be the example here, and GPUs are effectively very large floating point vector units originated from the graphics markets, where what you have to do is update pixels on a screen, which are floating point numbers, and each one of those can be updated separately. So you can do them as a vector operation where you can do the same instruction on multiple bits of data at once. And that means that if you have a code which can easily fit in that sort of vectorization model, then you can get really quite high performance on the GPU compared to CPU, because it's a more specialized processor with more computer hardware dedicated to that floating point operations. So GPUs are another way you can look at a single node performance optimization. You add a bit of hardware or a number of bits of hardware into your node that give you increased performance for your application, and definitely applicable to a wide range of nodes for a wide range of codes, particularly machine learning codes, to give you good performance. But of course, there are downsides to GPUs as well. So they can be harder to program, or some applications aren't amenable to efficiently using GPUs. And the way they're structured, you often have to move data backwards and forwards between the CPU and GPU, which can be an overhead as well. So they're not suitable for all applications. I see there's a question in the chat. Is threading limited across the node if you're trying to run something like BLAS, which would draw significant power due to preventing throttling? So threading is, okay, this is a slightly complicated question, I think. Threading is not limited across the node in the sense that you can run one process and spawn threads across the whole node. You can use all 128 cores with threads. And if you want to use the hyper-threads, you could use 256 cores effectively with your threads for something like BLAS, so the algebra operations. There are a couple of caveats to this. One is that, as we'll see, once you go across processor boundaries, you may see performance impacts because you start to move into different memory hierarchies, and there can be problems there. And the AMD processors, just like the Intel processors, have this idea of performance variation depending on what the processor is doing. So Intel had this concept in their processor of turbo boost. So your processor could go faster, it could change its clock speed if it wasn't doing much. And then if you fill the processor up, then it dials back the clock speed. So it sits inside some kind of thermal and power limits. The AMD processors will do something similar. So if you run things on the whole 128 cores or 256 hyperthreads and you're using them intensively, then it will not limit the threading, but it will have scaled back its clock frequency to sit within its power and thermal limits. So that won't reduce your performance, but it will mean that actually you may get slightly better performance per thread if you're not filling up the whole system, if you're not filling up the whole processor, because it may be able to go faster than that. So if you have a problem where your application, if you've got a problem where you're using a library like BLAS or doing matrix operations yourself, or matrix vector stuff, and you're doing it with threads, you may see better performance using a smaller number of threads than you do if you go up to the whole node, because of some of these effects. Yeah. Okay, so I'll try and zip through these so we can actually get a break and then get onto the practicals. But as I've already discussed, memory is a substantial performance inhibitor to processors, because the latency and the bandwidth is sort of much lower than what the processor itself can deal with. But we have these caches to try and bridge this gap. So cache memory is much faster than main memory, but much smaller, and it keeps copies of recently used data. And generally, caches exploit this idea of temporal and spatial locality, i.e., data your program has recently used is probably going to be used again. So let's store that locally. And near data that you've used in memory is likely to be used again, likely to be used soon. So this idea that if you're going for a big array, if you've loaded the beginning of an array, then you're going to use the next element of array and the next element and the next element. And so if your program can fit into this sort of logical structure of temporal and spatial locality, then you can get good performance from the processor because you can leverage these caches. If you can't, then you end up reducing your application performance because you end up limited by the main memory speed rather than the performance of the processor itself. And so we can see, theoretically, we have these ideas where the processor can run at a certain speed, but main memory is much slower than that, so order of hundreds of cycles slower than the processor. And then we have these levels of cache which try and bridge that gap. So the main memory is big, but cache is small, and the higher up the cache hierarchy you get, the faster the cache is, but the smaller it becomes. Caches are really quite sophisticated, but this is all done for you in hardware, so you don't have to care about that. But you do want, we do for performance application, care about whether we're using that cache efficiently ourselves so that we maximize the cache reuse. And one of the lectures tomorrow will go through this in more detail. Memory systems will also go above and beyond just standard caching and do things like prefetching for you. So they'll notice that you're loading data in a certain pattern and prefetch that data for you. Again, this is done in hardware and so there's nothing you have to do, but you can actually do some prefetch optimization yourself for applications if you want, because if you know that your memory access pattern is not simple and the hardware is not likely to spot it, you can probably write some prefetch functionality which will do that for you rather than it happening automatically. So as I already discussed, caches and prefetching works on this idea of locality, and are very important for sort of speeding up data accesses. Now caches work on this idea of blocks or cache lines. So we don't load and store individual bits of data on modern processors. You know, we don't load a 32-bit or a 64-bit integer or 32-bit or 64-bit floating point number. We load cache lines or cache blocks, which is generally much larger than an individual bit of data, maybe somewhere between 32 and 128 bytes. And so that means that we're generally loading up chunks of our data at once to use in a cache. The cache will always cache on reading data, but the different processes do different things when you write data out to memory. So some might write cache on write, and some may just write directly back to a main memory. And this kind of performance implications across processors, but we'll talk more about that tomorrow. If you try and read data from memory and it's not in the cache, because what will happen is the processor goes and asks for some data, and the memory system goes and looks in the cache first. If it's not there, that's what's called a cache miss or a read miss, and then it will go off to main memory. It will load in the cache line that data is inside, put it into the cache, and then load that into the processor from there. Caches have this done. You know, they've got to, the hardware just has to have some mechanism for taking data from memory and assigning it to somewhere in the cache, so it's easy for the processor to find. And so it has to have these quick, efficient search mechanisms inside the hardware. And so the way this is generally done is there's an idea of cache sets, and each block of memory will map into a cache set, and then you can put multiple bits of data into the cache at once. So the idea here is you go and load up some data from memory. The memory system works out which cache set that memory will map to, and then you'll go and put that particular memory you're loading up into one of those lines in that cache set, one of the blocks in that cache set, and then that it will stay there. And now different bits of memory will map to different cache sets, and then in each set you have multiple blocks, so that you can actually store multiple maps to that memory at any one time. And the number of the size of cache lines, the number of blocks, and the number of sets, the number of sets and the number of blocks in those sets varies across processor designs. When you get a cache miss, you then of course have to replace existing data in the cache with your new data you want to load up, and how this is done will vary across processors as well, but generally it's least recently used. So the processor is keeping track of data that's been used in the cache, and the one that hasn't been used recently will get overwritten or saves back out to memory, and away we go. Now we'll talk more about this cache, the specifics of cache tomorrow, particularly including the write through and write back stuff. But cache performance, cache hits and cache misses are very important for getting good performance for applications on modern processors, because if the data is not in the cache, then the processor has to wait until that data is found before the instruction that depends on that data can run. And this is one of the reasons that we'll get these pipeline stalls. So the processor will try and keep going and execute other instructions, but it can only go so far until it runs out of registers to store temporary data in, and then the pipeline will drain down until this new instruction comes, this new data comes in that it can work on. So using these caches efficiently is important. That whole memory stuff sits inside this concept of virtual memory. So modern processors and modern operating systems run in a scheme of virtual memory, where programs are mapped onto the physical memory from a virtual address space. And this is done for a number of reasons. One is from sort of a security usability point of view. It lets you separate out individual applications that are running a processor and in an operating system to keep their data separate in virtual memory spaces. But it also lets you map different applications to different parts of a memory and move them in and out of memory as required. So most computers will let you do this thing called swap memory, where you can actually have more data loaded than you have physical memory, and some of it's swapped out to disk. That's very beneficial for a lot of applications, because it lets you open up a document and still keep other programs running, but not crash the computer when you run out of memory. In reality, for HPC systems, we don't use this functionality, so we don't allow swapping of data out to disk. We'd rather applications crash if they run out of memory, rather than run 10 times slower. So we don't allow that. And actually, if you run an application, you run out of memory, you'll see these sort of errors such as out of memory OOM killer and OOM errors, which say you've run out of memory. But we still use this concept of virtual memory. And so application space, all the memory operations are done in virtual memory, and then they're translated into physical memory. So spaces in actual data, in actual RAM, when they're loaded into a processor and when their instructions are operated on. And this is done through the load store unit and through specialized hardware in the processor to deal with this. There's also a special buffer for these mappings between virtual and physical memory. So something called the TLB, the translation look-aside buffer, is a hardware cache which stores these mappings between the virtual memory space and the physical memory space. And that means that once you've loaded up some data and you're reusing that data, you don't have to recalculate these address offsets between virtual and physical space. Now, all this is done for you by the hardware, by the processor itself, but there can be times when the TLB and TLB pressure can inhibit your program's performance. And so there can be times when playing around with how the virtual memory is used and set up on your system can give you performance benefits, mainly around page size. So virtual memory is organized into pages. Pages come with different sizes, somewhere between 4 kilobytes, but then can be much larger than that. And the translation between pages and physical memory on the system is done through this TLB system. And so if you're having problems with an application where you're losing performance because of this virtual address translation functionality, then you can change your page size, give you a larger page size, and give you fewer TLB misses. We've talked about prefetching already, and caches. Cache coherency starts to be important when you move from a single core to running a program across multiple cores. So an individual single program running on a single core, it can work on its own data with no problems. When you start to move into the arena of multi-threaded programming, something like OpenMP, where you've got a single program and then its workers collaborate and can share data, then we have to start caring about coherency between those different workers, so that if two workers are working on the same bit of data, they get correct data when reads and writes happen. Now, the processor will do cache coherency for us, and it does it through the memory caches that we use. And this can have performance impacts as well. And Mark will talk more about this in the OpenMP lectures tomorrow. But there's really quite complicated or complex functionality in the processor to deal with this. And it's one of the reasons why it's very hard to build a very large shared memory system, because the coherency between cores or between processors becomes expensive. And one of the places you can see this giving performance impacts is something called fault sharing. And so one of the things that Mark will talk about in the OpenMP lecture tomorrow is fault sharing and performance impacts that can have for OpenMP applications. Beyond a single core and a single processor, then we can also look at shared memory between cores and between processors on a single system. And so this is what we call distributed shared memory. But because we have two processors on a ARCHER2 node, they each have their own memory, but it's shared across the node. We have this concept of slow memory and fast memory, or what we call non-uniform memory architectures, NUMA effects, in that a core can access memory which is local to its processor faster than it can access memory which is local to the other processor in the node. And so these NUMA effects are important to us, in that it means that applications really need to make sure they are allocating and using memory locally to their processor rather than remote memory on the other processor in the node to get the best performance. So the main problem for these NUMA effects is that access to remote memories takes longer than local memory. And so we have to be careful when we're doing our allocation of data for applications where you may be able to share memory between the processors, to do it in what we call a first touch way. So we make sure that the memory is allocated locally to the processor where the worker is actually running. And again, Mark will cover this in more detail tomorrow in the OpenMP lecture. So for the ARCHER2 nodes that we have at the moment, and that we'll be playing with today and tomorrow, as I've already said, there are 2 processors per node. Each processor has 64 cores. So for each of the AMD, if you're interested, the AMD Rome 7742 processors, each processor has 64 cores, and they're connected together by this infinity fabric to give you fast interconnect between the processors. Each processor has its own memory attached to it, so it's got 128 gigabytes per processor, giving you 256 gigabytes for the whole node. Actually, any core can access any of the memory, but it's faster for a core on this processor to access its local memory than it is to access the memory attached over here. Now, these AMD processors are actually even more complicated than that, in that each processor is split up into 4 groups, and each group has 16 cores in it, and they have it's faster to talk inside your 16 cores than it is to talk to any of your neighbors on the processor, and then than it is to talk to the neighboring processors. So actually, these AMD processors have multiple NUMA regions on the non-uniform memory access times. You're quicker to talk inside one of these groups of 16 cores and share data in there than you are to share data between groups of cores on the node, on that processor, and then between groups on separate processors. So we have this sort of 3-level stage hierarchy in access costs. What does that mean for your application? Well, for OpenMP applications, it means that if you can stay within these 16 core regions and you can properly sit inside them, then you get better performance than if you're spread across these 16 core regions. And again, for something like your MPI program, it means that if you're doing messages between processors, then making sure you're communicating locally between local cores can give you better performance than remote cores. The node also actually has two network ports on it where you attach to the Cray network, one per processor. And now we're not looking really at network performance for this course, but then that does also means that it's beneficial to have MPI processors if you're doing that kind of program on each processor, so you can efficiently access both memories, both networks from your application. Yeah, the proper name is the AMD EPYC 7742 processor. It has 64 cores. It has a floating point, as a clock rate of 2.25 gigahertz, and it has 2 floating point vector units per core. This gives us each floating point unit can do 256-bit vector instructions, which means we can do 4 floating point operations per unit, which means we also can do 2 floating point fuse multiply add operations per clock cycle as well. We'll talk more about those tomorrow. But so that means overall, each node can do about 4.6 teraflops of floating point operation, which is really quite high. And there are quite a lot of floating point operations per node theoretically. Now that does depend on you efficiently using these vector units, because there's 2 of them. So you get 8 times performance if you use the vector units than if you don't. And it also depends on your code being amenable to this FMA instruction, fuse multiply add, which a lot of codes aren't. So in reality, most applications are not going to see this anywhere near this 4.6 teraflops of performance. But what we're aiming to do on this course is get you closer to that than not. Each core has its own level 1 cache, which is 32 kilobytes, and its own level 2 cache, which is 512 kilobytes. And then each set of cores, 4 cores, shares one level 3 cache, which is 16 megabytes, 4 megabytes per core. And then these are stitched together to give you a full L3 cache across the whole node. There are 256 gigabytes of main memory per node. At the moment, we may have, once the full system is installed, we'll get these 512 gigabyte nodes as well. And as I said, this is 8 NUMA regions per node, 16 cores in each, 4 per socket, 4 per processor. Now, that's all quite complicated. Most applications, you don't have to care too much about this. It's detail that won't impact you, but for some applications, it may impact your performance. And if you're interested, the latencies on the L1, L2, and main memory caches for this processor are, it takes you around 270 clock cycles to load data in from main memory. If your data is in L3, it will take you about 40 clock cycles. If your data is in L2, it will take you about 12 clock cycles. And if your data is in L1 cache, it will take you about 4 to 8 clock cycles. So you can see the relative performance benefits of being able to stay within these different cache hierarchies. Memory bandwidth is proportional to memory regions on the processor. So each processor has these 4 memory regions. There's 8 in total, 16 cores per memory region. But to get the full bandwidth, memory bandwidth of the processor, we need to be able to use all these memory regions at once. So if you're underpopulating, i.e. if you're not needing to use all 128 cores, then it may be beneficial to scatter across the processor to give you improved performance. And then, yes, NUMA software and NUMA performance, so this non-uniform memory access stuff, means that going between processors is slower, and going between these memory regions is slower. So NUMA-aware application programming is beneficial to give you good performance. Okay, so any questions about that? Now, I appreciate there's a lot of detail in there and a lot of things which won't necessarily make massive amounts of sense if you're not used to performance programming and computer hardware at the moment. The idea is just to give you a background across the process and across the node at the moment, and then we can come back and look at it in more detail when we look at things like optimizing with the compiler, optimizing by hand. And we can see which of these different features in the hardware we're targeting with our specific optimizations. So this is much more of a reference than us expecting you to understand and memorize any of this stuff up front. Having said that, is there any questions that anybody has at this point? Now, whilst you're thinking of your questions, obviously I've gone massively over time for this lecture, so we're completely off the timetable at the moment, and I've also talked to you for too long, so you'll need a break from me. So what I suggest we do is we take a break. Let me just check my timetable. 1 second. What I suggest we do is go off piste, and we're going to take a break now. And what we'll come back to do is we'll come back at 12, so give you a nice break. We'll come back at 12, and we'll start the first practical 12 till half 12, and then I'll talk the I'll do the next lecture 12:30 till 1, and we'll have our lunch break then. So we'll take once I've answered these questions, which thanks for asking them. I can see they're coming in now. Once I've answered these questions, we can take a break from now until 12, and then at 12 we'll reconvene, and I will tell you the instructions for doing the first practical. Okay, let me get back to the questions. So what's the expected cycle cost of burst buffer compared to main memory? From Michael. Great question, Michael. It's not a question I can answer at the moment because actually we don't have a burst buffer, and we don't know the performance of a burst buffer at all at the moment. There's a sort of a wider question there, really, which is what's the access cost from going inside a node to going outside the nodes, i.e. going somewhere which is not inside your compute node, going over the network, because effectively you go to burst buffer, or you go to another node over MPI, or you go to a Lustre file system. All of that is going to go across that network that we're using, the Cray slingshot network. And effectively what you're asking is, what is the single message latency across that that network? And so that is somewhere of the order of 2 microseconds. Now, I can't off the top of my head converting that into clock cycles, but I think we're talking of the order. I will do the conversion later and get back to you, Michael. I think we're talking on the order of a few thousand clock cycles. Well, maybe a few tens of thousands of clock cycles to do an initial network message. So to send a message from your node to somewhere else, be that the burst buffer or another node or the Lustre file system. So that's the order of what we're looking at there. I'll do the proper calculation and let you know what the actual overhead is in terms of clock cycles, but that's the latency you're going to be looking at. We expect anyway that the burst buffer hopefully will be able to work within the full network performance that we have. But until we get our hands on it later in the year, we won't actually know. And then there's another question, curious to know how the memory bandwidth and peak performance per core compares on Intel versus AMD sockets. So this is quite a broad question. You'll see actually tomorrow in Mark Bull's OpenMP lecture, then he has some performance comparisons of bandwidth on here. Per core is a little bit complicated because different processors have different performance where we see cores, particularly if you just compare an Intel to AMD in general. If you wanted to compare Archer to Archer 2, we could do a specific comparison there. And then it sort of depends a little bit on what you mean by per core, because if you run a single core, you can never get the full memory bandwidth of the processor. But if you run a certain number of cores, you can get the full memory bandwidth across the processor. However, if you wanted to do a bulk comparison between a current Intel processor and a current AMD processor, the current Intel processors have 6 memory channels per processor, and the AMD ones have 8 memory channels per processor. And so what we're looking at is something like 160 gigabytes a second for a whole processor on, well, a whole node on Intel, and something like 220, 230 gigabytes a second for a whole node on AMD. That probably means about 80 gigabytes a second per processor on Intel and about 120 gigabytes a second per processor on AMD. And then you can get that for a subset of the cores, but not for an individual core. So it's a little bit of a complicated benchmark to do. I do have some numbers somewhere, not in these slides. I do have some numbers that I can look out for you, which will tell you the per core bandwidth for an AMD versus a per core bandwidth for an Intel processor, and then how many cores you have to use to then get the full processor bandwidth. But so does that answer your? Yeah. So the core counts on the. It's an interesting question about the core counts on Intel versus AMD sockets and what a fair comparison is. This is why we tend to do processor comparison, not core to core, because the different processors have different numbers of cores in them. So it's easy to say, okay, the processor is the package. Let's see what one processor looks like versus another. But yeah, for some applications, it very much matters what a core to core comparison is. But then you have to be careful, because the core-to-core comparison will change if you run things on 1 core or 2 cores or 4 cores, because the processors react to what you're running. So it gets a little bit murky there. But yes, core-to-core, I'll look out the data. Processor, the AMDs are about somewhere between a quarter and a fifth faster in terms of memory bandwidth than the Intels. You know, if you're comparing similar spec processors. Evgeny is asking me, having extra NUMA levels, would you speak of local, remote, or is there some established terminology? There isn't an established terminology as far as I'm aware. There is, as you say, local, near, and then local remote, I think. Is what I think of them. So there's sort of local, which is your 16-core group on a processor. There's local near, which is everything else on that processor, and then there's local remote, which is everything else on the other processors in the node. But I mean, that's just my terminology. The latency for reading data, which is in an L3 cache on the same NUMA sub-region, is different from an L3 cache somewhere else on that processor. It's not as bad. It's nowhere near as bad as going onto main memory. It's nowhere near as bad as going onto another processor. I don't have a number off my. Let me just check what the number is. It could be in those links that have been shared, but I think I have. Let me stop sharing as well, so you don't have to see all my nonsense. Stop sharing. But thanks for all these questions, by the way. It's great. It's great to have people asking questions. So looking at the latencies that we've seen for between these groups on the same processor, I think as I said, the latencies to L3 cache, you're about around 40 cycles, 37 cycles from a core to L3 cache. From a core to another L3 cache on the same processor is more around the 100 cycles. And then if you were going to a different processor, then you're sort of starting to get to the level of going out to main memory costs. So it's sort of half the cost of going to main memory or to the processor of those values. Anybody have any other questions? It'd be great to hear them. And as I say, you don't have to do them here in the chat, but you can send me a private message in the chat, or you can email me. Other than that, we'll come back at 12 and we'll start on the first practical. And thanks for coming along. Apologies, it was such a long lecture. Okay, apologies for the delay. The practical sheet here is this one here. There's a number of exercises on it. The first one we're going to do is exercise 1, which is the placement streams benchmark, and I'm just making sure the code is in the correct place for you, so bear with me on that. And then Luca, I will answer your question in a minute. Apologies, I will get onto that. But let me just make sure the code's in the correct place, and then we should be good to go. Okay, everything should be present and correct now. There should be a file here. That's all the practical material we're going to use for today and tomorrow, and you should be able to get that, copy it into your work directory on ARCHER2, and set yourselves up. Now, this first practical here, let me share the PDF so you can see what I'm talking through. So this first practical here, excuse the sound of aircraft flying over. Here we go. So it's the practical sheet on the repository for this course. Here it comes. This first practical here, which you can go through. Really, what we're looking at here is this one called placement, and it's not designed to be particularly taxing exercise. It's really just designed to check that you can get up and running on the system, and you're happy with your access, so you can make sure that you can run jobs, and that you can log into the system. Basically, what you're going to do is log into a system, then copy this file here, this sno.tar, into your work directory. And I should say, ARCHER2, like Archer before it, has got a couple of file systems. It's got a home file system, which you go into when you first log in, and it has a work file system as well. Now, the home file system you can't run jobs from, so we're going to do everything in the work file system today. If you are using a course account, i.e. TA 013, when you log in, you will end up in a directory like this here. home/TA013/TA013/username, where the username is the account you're logging in through, and that TA013 is the project name on ARCHER2, and you have an equivalent directory called work, TA013, TA013, which is the work file system, where you can go and do all the work from here. So if you were had logged in, then you just normal, you would just do cd work TA013, TA013 username. Of course, replacing username here with your actual account name that you're using on the system, and then you can do this, run this command, copy work I'm hoping it works. Z19 shared SNO.tar here, and then unpack it by using this tar x here. SNO. These are the commands you need to do. And then for the first exercise, then you would do cd archer2 opt. And sorry, the font here is not brilliant, but that's an O, capital O, archer2, capital opt / placement. Then let me just try this myself on my ARCHER2 login. Yeah, once you're in placement, you should just be able to type make. Worked for me so far. And then that should build a program, and then we can do this sbatch command. Let me just scroll down my PDF. Wrong PDF. This sbatch command here to run our application. Now I'm just looking at the reservation name so we know what to put in here. And okay, the reservation name is TA013_92. Then that should work for you. So you should be able to do sbatch double dash reservation equals TA013_92, and then the name of the batch file, run streams, and then that should submit a job for you, and you should get some output from it. Now, I'm using my account, not a training account in ARCHER2. In the ARCHER2 TA013 project. So mine will look slightly different, but I'm going to have a look at the batch script now and talk you through it. But if anybody, okay, so I'm getting line break errors. I think, are you copy and pasting directly from this chat window? Okay, let me check that. Batch script contains DOS in the run streams. Okay. Apologies. Give me a second then. Let me try this out for myself. Okay, that is slightly annoying. It has. Let me see if I can fix these line errors. Copying it from one system to the other has broken my batch script. And DOS to Unix would normally do it for me, but I don't think we've got DOS to Unix on the system. Yes, it has been at Windows at some point. Oh, thank you, David. So let me fix this, and you can copy it yourself so that we don't break. So you don't necessarily have to do this yourself. I can update it in the thing, so you can copy the whole tar file again. Okay. Thanks everybody for helping out on this. It's very useful. Let me just check none of the other batch scripts are going to do the same. And then I'll create a new version of this so people can copy if they don't want to run this themselves. Now, I did say there would be some snagging we had to do in the first run of this course. Of course, I had checked all these before, but then copied them to my Windows machine to then copy them onto the Git and made some changes, and obviously that broke everything. Okay, Stephen, so invalid account or account partition combination specified. Yeah, let me have a look at the batch script again. Okay, so this is my fault here, so apologies. In the batch script itself, you need to change that XXX, yes. So I haven't put this in there. But if you have a look in the batch script, there is a line like this in the batch script, which says, it says XX, and you need to, as people have been saying, you need to change that to the TA113. Effectively, is just telling Slurm batch system that we're using to run our job what account to charge this to and what account to check that there's budget in. So sorry for that. That's something that I need to change in the handout. Now let me just share my screen briefly. And I appreciate for some people who have been Archer users before or heavy users of HPC systems, all of these things that we're doing are second nature to you, so you don't need to worry about that. It's not something, but there will be people on this course who have not heavily used these kind of systems before, so this can be a little bit of a learning curve. Gunnar, do I have a script to visualize the XML output? I do have a script to visualize the XML output, but I haven't given it to you because we don't need to do that for this practical. If you're interested out with this practical for that, drop me an email and I will send you the visualization script for that because it's something that I use separately. I'll put my email address in here again. But in reality, for what we're doing in the practical, we can just look at what's produced in the Slurm output file. Anyway, we can see here the batch script that we're running here. Now, this is slightly different to yours because I'm in my account, which is in the Z19 project and not the TA013 project, and I'm not using your reservation. But apart from that, it looks exactly the same. What we're doing, just for those of you who are not familiar with Slurm or batch systems in general, this here is specifying the setup for my job. And we're using Slurm now on ARCHER2, which is slightly different to what we had on Archer, which was PBS, but it does very similar things. What I'm saying here is I'm giving my job a name. This doesn't really matter, but this is just so I can see it in the queue easily. How long my job will run for, maximum runtime. I'm wanting one node. And then here I'm saying I want to run one thing per core. So this is just telling it that I don't want to oversubscribe things. I'm saying exclusive here. Actually, I don't think I need to put this in because I don't think you can share nodes on Archer anyway. But this just says, I want the whole node. I don't want anybody else using the node. And then we're using a standard partition and standard quality of service setup. Why are these interesting? Well, when we get the full Archer system, then the standard partition, we will have different partitions, which is sort of different groups of nodes, including the large memory nodes will be in a different partition or a separate partition. So you can say, I want to go into the large memory nodes. And also when we'll have a small GPU test system attached to this, you'll be able to go into the GPU partition. So this is how you select things. And then the quality of service lets you specify different things for the job. So we have a debug queue where you can get jobs run quickly, if small jobs run quickly, and that's got a quality of service QoS of short. And we have a large job queue where if you want to run long jobs, there's a large QoS as well. So I think we can see what we are. Yeah, okay, so you can ask to learn what the QoS are. Now on Archer we've got normal and standard, which I think are the same thing. There's a long one, which is I want to run jobs so more normal jobs will only run for 1 day. You can also run long jobs for up to 2 days using the long QoS, and you can use this short QoS to access the debug queue. There's also a high priority QoS, but I can't remember what that's used for at the moment. I'd have to look back on the Archer website. Anyway, that's what those QoSs are. Then we need this module load EPCC job environment as part of our script to set things up. And then I'm setting up things for the job. And down here, what I'm doing is I'm running 2 programs. One is this program called XTHI, which is just a little helper program which prints out how processes are mapped to cores, and it can be useful to check that we're using, we're binding in the correct way. Now, if you're running a normal job on Archer and you're using all the cores on Archer2 and using all the cores, then you don't generally have to care about bindings. You just put, the system will just do the sensible thing for you. Because we're underpopulating here, I'm only asking for 16 processes per node. Then I want to specify how I want to see how it's, which cores it's putting those 16 processes on. So I'm running that first, and then I'm running my streams application. And this is a version of the streams benchmark, which is a memory bandwidth benchmark, which we've written here, EPCC, which does it in parallel on the MPI and lets you look at node level and process level benchmarks. And then there's some other stuff here, just helping with the placement, including this thing here, -C1, which says, for each process I'm running, give it 1 core. And so when I run it like this, what I should get is an output which says, let me see if I've run it here. Yeah, okay. I've run it here. I've got an output which says, actually, I ran the XTHI program and it said, first process is going to run on the first core, on the second core, and the third core. So you can see here, when I'm running my 16 processes, they're all sitting inside that single NUMA region, on the first NUMA region on the first processor, and everything else is free. And then this is the output from my streams program. And I can see per process, I got about 1.8 gigabytes a second memory bandwidth. I mean, you don't have to care what the difference between copy, scale, add, and triad are. They're just slightly different operations. And then on a node, so adding up all the processes in a sensible way, I got about 28 gigabytes a second memory bandwidth. So that's from one of these NUMA regions, full NUMA region, I got about 28 gigabytes a second. Now that's not very good, because I know the whole node will do 200 and something gigabytes a second. So I can see that from a single NUMA region, I'm not managing to get the full performance of my node here. But then we've got 8 NUMA regions in the processor. So if I use more of these, I should be able to get better performance. Now, streams is a little bit of a benchmark you need to tune. And actually, I've not tuned this one very well. because really I'm not quite using enough memory here to give you good benchmark figures, because actually to get reliable benchmark figures for stream, you need to have the total memory per node as something like 4 times the L3 cache size. And the L3 cache size here per node is 512 megabytes, because these processors have got quite big caches. They've got 256 megabyte L3 caches. So actually I should really double this or triple this. Now I can make that change here in the make file. You don't need to do this because it's the actual results are not, the absolute results are not actually important for you. But if you want to, you can change the last level cache size to being a bit bigger, rerun it and see what happens. Now what I want you to actually do is then change this, instead of running on the first 16 cores, to then actually spread it out and use all the cores across all the processors in a node. And I can do that by saying actually give each processor 8 cores to start with, so changing this -c from 1 to 8. And I can rerun my code and I should get various outputs. So let me have a look at my output when I change the cache size. So you can see I'm now benchmarking on about 1.8 gigabytes of memory. That's close enough for being 4 times the size of the L3 cache. And you can see here I'm still getting similar performance. I'm still getting about 1.7 gigabytes a second per core and about 28 gigabytes per second per processor. However, if I change that and then spread my processor out across the node, you can now see that each processor has now got 8 cores to use. So the first processor is using cores 0 to 7, the second processor is using cores 8 to 15, and so on, all the way up to core 1 to 7, which is the last physical core. And now we can see that in this case, I've now sort of, by an order of magnitude, got better performance. Now I'm getting up to about 10 gigabytes a second per core, and about 160, 170 gigabytes a second for the whole node. So 16 times 10, I'm getting about my good performance there. So we can see that just using a single NUMA region, we can't get all the memory bandwidth as node, but using all the NUMA regions, we're doing well. But actually, I know I'm not probably doing as well as I could do here, because I think this node should be able to do 220, 230, 240 gigabytes a second. So maybe we just haven't quite got enough processors to do this. So let's see if we run 32 things instead of 16 things, and change the number of cores we give out per process to 4, because we're using 32 now. 4 times 32 is 128. And if we run that, see if we get closer to our performance that we're expecting here. Now, might take a little bit of time to run. Anybody having problems running this themselves, either in the reservation or just compiling it or getting access to the code, please do let me know, because this is now the time for us to fix these issues. And it's fine if you don't know how to run a system like this. Many people have never run a system like ARCHER2. We're not expecting you to have done so, but now is a good time for you to say if there are issues with running applications. Do interrupt me, because I will just keep talking. So now we can see we've got 32 things running. Yeah, 1 second. 32 things running, and now you can see my performance has actually per process has gone down. So per process, I'm now at about 7 gigabytes a second, but per node, I'm using about that 240 gigabytes per second. So this is the configuration I've done to run 32 things per node, but give each one of them 4 cores. Does that help, Helen? Is that what you want to see? What's the error? Okay. So if you go to 4 times 32, you get this error. But if you go to 8 times 16, you don't get the error. Is that correct? All right. So even on 1 times 16, yours is not working. You get requested no configuration is not available. And does your top of your batch file look like this one for you? Ah, okay. Can you try submitting without the reservation and see if it works without the reservation? Because it sounds like there might be an issue with a reservation. Now, my jobs are running pretty quickly at the moment anyway, so I'm not sure. Okay, it works without the reservation. Right. I will investigate that. Let me see. Slightly annoying. I mean, it should work fine with a reservation, but for now, leave the reservation off. I think actually I might know what's going on with that, but I need to contact the system team to sort that one out. I think there may be unfortunately I can't test it because I don't have an account in the project, which is a bit of an oversight on my behalf. But fine, leave a reservation for now. We'll fix that for the next practical. But thanks for letting me know. Very useful, and I'm sorry it caused you some problems. Anyway, so what we can see here, hopefully, is that hopefully you've been able to run it and get some of these numbers out, and you can see that actually to get all the memory bandwidth from a node, for this application at least, we need to have at least 32 processors, and they need to be spread out across the node. If I just run the 32 processors and I run them all on, the first 2 NUMA regions, first 2 16-core groups, then you can see that we only get, a quarter of a memory bandwidth from the nodes. I'm getting 56 gigabytes, 55 gigabytes a second, whereas I know we can do around 240 gigabytes a second. So we can see here already that if you're underpopulating, if you're not using all the cores in the node, and you don't need to use all the cores in the node to get that memory bandwidth at 240 gigabytes a second, then making sure you set up your application to run in the right way is going to be beneficial for performance. And if your code is memory bandwidth bound, it can be a factor of 4, a factor of 8 faster. Just making sure you're running with the right number of processes on the right placement. So have a play around with that script. Run these jobs as I've done. You could try using 64 cores and 2, so that would be changing C to 2 and this to 64, and then try for both of them and run that and see what you get. And the same for 1 to 8 and 1, and 1 to 8 and 1. And then also try 64 and 1 and 64 and 1 and see what performance differences you get. And once you're all happy that you can do that, can you please use the raise your hand button in Collaborate here, which is the button down near the microphone and the share video at the bottom left of the bottom central of the screen. If you can click your raise your hand like I've just done now, then at least I can see when people have finished the practical and we can move on to the next lecture. So it's a great question. Why is filling up the processor improves the memory bandwidth? Let me share the slide from the last lecture that we had, and we can talk about that. So if you remember, our node is the big blue box for ARCHER2. Each node has two processors here, two processors. Each node has two processors here and here. And so let me scribble on this. This is a processor, and this is a processor. There's 64 cores here and 64 cores here. Now, inside each processor, there's actually these groups. That's one group there. That's another group there. That's another, group there. And this is another group here. So there's 4 groups inside a processor. And each of these groups really has its own memory attached to it. So it has its own set of memory chips dedicated to it. And accessing that memory is done through these processors. So this process can access its memory. And so if we put our 16 processors all in this one place, then they're all going to be accessing the same memory, the same subset of the memory in the system, and they can only get the memory bandwidth over those lanes. Okay, they're not using any of the memory bin. Now, we could set it up in such a way where we forced each processor to allocate memory off for different groups. If we did some more programming, it's a bit more complicated to do, but you can do that. But by default, a process uses the memory that's closest to it. All the cores are sitting in one of these groups. There's all 16 cores in here, all 16 processors, so they're only using one memory bandwidth. Whereas if we can use all of these groups on this processor and then all the groups on this processor, we actually get access to 8 times as many memory lanes, memory channels, and then we can use the memory bandwidth of all those channels simultaneously. So instead of putting all 16 in one here, we spread them out and put one process here. We spread them out and put a couple of processors in each place, 2 processors in each place, and that gives us access to all the memory channels, and that gives us access to all the memory bandwidth. Okay, so does that answer your question? Cool. So as I say, once you're happy, you finish the practical, you're happy it works, you can run happily, then please do put your hand up in the collaborate session, and I'll know we can move on. If you still have problems, and there's still things not working, that's perfectly fine. Just let me know, email or in the chat or in the private chat, and we can come and help you. But people always have teething problems getting onto the system, so don't worry about it. Now is a good time to sort it out. Whilst we wait for that, I will load up the next lecture. If there's any other questions, do let me know. Okay, so hyperthreading, great question. So we have 128 physical cores in the node. Hyperthreading doubles that. So we have up to 256 threads we can run in the node. By default, Slurm will not, because I don't know if you remember, but in there, or you've noticed, there's this thing called, I've put in my batch script called hint no multithread. So there's this flag I've passed to Slurm saying don't use the hyperthreads. initially. So what Slurm will do is fill up the physical cores first. Because I'm only ever asking for up to 128 things, I don't ever go into those hyperthreads. I could run up to 256 things, but for this kind of benchmark, the streams benchmark, it wouldn't help me, because once I go into a hyperthread, I don't get any more physical bandwidth. I just share in the bandwidth of those physical cores. So it doesn't benefit this particular application, because all it is a memory bandwidth benchmark. So it doesn't help me. But if I wanted to, I could run up to 256. I could turn off this hint no multi-threading, and then it starts get a bit more complicated on how you bind. You make sure, how you choose which hyperthreads to run on and which physical cores to run on. But there's more in the ARCHER2 documentation about that. Does that answer your question, Gunnar? Yeah, so the reason you're seeing about 338 gigabytes a second is because I mentioned that the version of a bandwidth benchmark I've given you is actually too small to get sensible numbers for an Archer. The amount of memory it's using is a bit too small. It's only using about 500 megabytes of memory, and actually we need it to use more than that. So let me just demonstrate that again. Here we go. If you look at the output you get from running your streams, you'll see something that says total memory required per node 457.8 megabytes or 0.4 gigabytes. For streams to actually be reliable, you need it to be on this processor about 2 gigabytes. So I changed my make file after I sent this to you. If you look in the make file, I've changed this last level cache size from 5 million to 20 million, recompiled and rerun it, and you should get bandwidths which are more closer to mine. What was happening for what you were seeing was actually you were starting to benchmark the L3 cache, because the whole problem size was fitting in the L3 cache. So you're starting to benchmark the L3 cache rather than the main memory bandwidth. Does that make sense? So sorry for that. I should have altered the benchmark before I sent it to you, but it doesn't really matter in this context. It does if you want to actually really properly measure streams memory bandwidth. Okay, so as I say, if you've managed, so we're not using easy build on ARCHER2 at the moment. The plan on ARCHER2, we're using modules. There's a module environment that we use. There is a plan here for ARCHER2 to use SPAC, which is similar to easy build, but not quite the same. It's not fully on there. The Cray environment is always a little bit strange for setting things like easy build and SPAC up on, so we're working on that integration. It's just not quite there yet. Does anybody still want to ask questions about the practical? If you're still continuing the practical, that's fine. What I will do is a reasonable number of people have finished this practical now. So what I'll do is move on to the next lecture. Then we'll have a break for lunch. Then we'll come back on and there's a practical associated with this lecture. But if you've not quite finished what we're doing now, or you're still having problems, you can just continue the practical we're doing now and go back to that. So really, really do please let me know if you're having issues. If you're having issues running for practical, or you don't understand it, or you don't understand part of it, because that's absolutely why we're here. Dilhan, it's not a trivial question at all. It's a great question. Why, if having more NUMA regions increases performance, why not have it by default? So having NUMA region, sort of spreading your applications across your process across NUMA regions does give you better performance, and Slurm can do it by default. I stopped it doing it by default by passing that -C1 flag into it to start with. So I automatically made it not do the best thing there, just to demonstrate the point. But there are cases where you don't want to spread across NUMA regions. There are cases where, because we know that sharing data between processors or threads inside the same NUMA region is faster than sharing it outside. As we've already seen, if you have to go to L3 cache and you're sharing data outside a NUMA region, it's about 4 times slower than inside a NUMA region. There are applications where very much you want the bandwidth, but you don't want to get that extra cost going across NUMA regions. So you want your processors or threads to be close together, and then just use more processors or threads to use all the bandwidth. So there's never any sort of one best solution for all applications. It's very application dependent. Any other questions? Okay, right. As I say, we can come back to this practical if you need it, but we'll crack on with this lecture so we don't fall too far behind the schedule again. So, keystone to performance optimization is actually profiling. So before we optimize, we want to make sure we know our application performance and know where the bottlenecks are, so that we can understand what to do to our application to improve the performance. Jumping in there and trying to make changes because we know cache blocking is good, it may give you performance benefits, but your application may not be memory bandwidth bound, it may not be cache bound. So we need to find out what your application is being performance is like. It may be your application is getting the best performance you could possibly get on a node, and there's nothing you can do to it. It may be that your application's got terrible performance and there's loads you can do to it, but without profiling, we can't answer that question. So profiling is analyzing your code to find out the proportion of execution time spent in different routines, and also the specific sort of hardware associated with your code. So basic profiling looks at what time is spent where in your application, and then more involved profiling looks at hardware counters and hardware resources and how you're using those. And so you can imagine things like trying to understand if you're getting hit by TLB buffer pressure, or if Supercalar processor instruction issue or register pressure is hitting you. You probably need some access to some more detailed hardware information. But if you just want to be able to look at the code and see if it's structured correctly, then you just want to find which parts of the code are being used most intensively. And fundamentally, this is all because there's no point optimizing bits of a code which don't contribute significantly to a runtime. Okay, so we need to look through the code, through profiling, work out which bits of the code are most expensive, and then try and optimize those bits. And then we can look at the hardware information to see if there's optimization we can do there. Profiling is the standard way of doing this, and it's something which is generally works by instrumenting the code at compile time. So the compiler will go through and add extra bits into your code, which are then run when your program runs and records what's happening. And because it's done by the compiler, it's usually controlled through compiler flags. Now, the reason we don't profile codes by default is because you're adding extra stuff to your code, you're going to impact the performance of that code. Because you're adding extra code in, you're going to make your application go slow. And there are different ways of doing profiling. We can do sampling, or we can do tracing, and they can have different costs. So really intensive profiling can really slow down your code. It can go sort of 10 times slower if you have all the profiling turned on everywhere. But you can also do profiling which slows your code down 5, 10% and no more than that. So, but that's why we don't do it by default. We only do it when we're ready, and we're not doing production runs, when we're ready to work out the code performance. Now, a standard sampling profiler will record number of function calls and the amount of time spent in each section of a code. A tracing profiler will do function calls and then amount of time spent per line of code, so it goes at much lower detail. It goes at a much lower level or much higher detail. And then we can also use tools that will return hardware-specific data, cache misses, TLB misses, cache reuse, flop rates, these kind of things. And these can be important for when we've got through, either for guiding your optimization, so working out what kind of performance optimization you need to do, or when you've done the basic performance optimizations, but you still want to get better performance, looking at really sort of more specific, more involved, and more in-depth optimizations. So as I said, many profiles work by sampling, and so what this does is it samples the program counter at regular intervals. Basically, your program runs, every 100th of a second, the program's interrupted, and it says, whereabouts in the program am I? Which routine am I in? Okay, there we go. And so this is a good way of profiling because it gives it's particularly low overhead. It doesn't add much in terms of performance cost. And for a long-running code and a not massively complex code, then it gives you a good statistical picture of what routines this time is being spent on. If a runtime is too small, or there's lots and lots of small function calls, this way of profiling won't necessarily give you the most accurate data because there may not be enough samples or enough samples of different routines to give you good statistics. And there you can use tracing instead, which uses much more detail on recording every time a function is called or every time a line is called, and it can have a higher impact on runtime and can produce very large amounts of output. Now, the standard profilers we can use in Linux and Unix are the prof and gprof tools. So we can have this -p flag when we compile or -pg flag when we compile. And that adds the extra stuff in from the compiler. And then you run your code and it produces an output file. And so it produces an output file mon.out for prof, so this -p flag, or gmon.out for gprof, this -pg flag. And then there's tools like gprof which let you view this output. And this is an example. I've compiled a code, added this one extra flag -p, and then I've run my code, and then my code produces an output called mon.out, and then I run prof in the name of my application, and it produces me this table here where it says 30% of a runtime was in this function called relax. Another 30% of a runtime was in this function called resid. Both of those were called 14 times. And you can see actually overall my program only ran for less than a second, so actually it's maybe not a brilliant profiling run disk because it's a bit short. But we can see that we've got two places here where nearly 60% of it, or 60% of a runtime is just in these two places. So if I'm going to optimize this code, these are places to go and look at. There's no point me optimizing the code, this read function down here, which only took 2% of a runtime, because even if I make it go a million times faster, I'm only ever going to speed up my code by 2%. Whereas if I can make these go twice as fast, then I'm going to make my code go a lot faster. And then there's other things in here. So actually we can see here this thing called mcount appears, and it's called 1.6 million times. This is actually the function that the compilers put in to do the profiling. So we can see that the profiling here added about a 5% overhead on my run. Actually, if you see these things like mcount appear a lot, if they're much more than 5%, it's a likely example that you've got quite a lot of overheads in your function calls. You've got too many small function calls. And then I've got other things in here, Fortran library calls to I/O stuff as well. So you can see actually about 10% of the time is being spent in file I/O, maybe more than that here. So that I could maybe look at optimizing my file I/O. gprof produces a similar thing, but you also get a call tree. So this function called another function called another function, which can be very useful to work out where the time is being spent. And as I said, the compiler introduces its own overheads to do the profiling, and these are often called monitor or mcount or mon control or something like that. And if you see that often in high up the function where the profile output, then that's evidence that you've got a lot of overheads in function calls, too many small function calls impacting your performance. So profile your code. Okay, profile your code yourself. Don't let somebody else tell you what's wrong with the code. You have a look at it for yourself. Profile the code on the hardware you want to run on. So don't profile on your laptop if you plan to run on ARCHER2. Profile your code on a full-size problem, because that's probably different from a small benchmark or a small test case. And profile your code as you optimize. So we see performance optimization as a cycle. You profile your code, you suggest some changes, you make those changes, you measure performance, you reprofile your code, and you go again. Now on Archer, we have access to Cray, which is a Cray profiling tool, which will do both sampling and function loop level tracing. It's quite a nice profiler. And we can use it in a number of different ways. We can build an instrument code, we can get a statistical, a sampling profile from it, we can rebuild and get a tracing profile from it, and those kind of things. If you've used Cray from Archer, you'll have maybe seen how to use it, and it's changed slightly on ARCHER2, but it's pretty similar. The profiling tools are generally loaded by default, but there's a couple of different ways we can use it. We can do Cray light profiling and Cray in-depth profiling. So perf tools, if we do this module load perf tools light, and then just make our application, rebuild our application as normal, make clean, that's all you have to do. Loading this module will have set the compiler to do the profiling. You build your code and then you run it, and then you get application output to tell you your top time-consuming routines and a simple performance profile. So something that looks a little bit like this. So this was something which came from me benchmarking the streams application you've just been running with Cray Lite. It doesn't, the output looks a little bit better than this in the job script. It hasn't come out brilliantly well here. But what we can see here actually is that we have, for the function calls that we're going on here, we've got about 60% of the time is actually sitting in spin wait and querying CPU mask. So actually, most of the time for this benchmark has been in querying the hardware setup. If we went down and looked actually in the user time, it's telling me that on line 121 is the most important line, and I've got some MPI barriers in here. But what you can see here, this is not very interesting output. What you can see here is it's telling me the amount of percentage of the runtime that is being spent by each one of these function calls, and possibly even down to a line level. And then it gives you some performance indication, some different commands you can run down here to say, actually you can get a full report out here, and you can get some call trees out here, and you can get a graphical interface using this AP2 command down here. Okay, so, and I appreciate we're going over time again as well. You can also do a more detailed thing. Rather than using perf tools lite, you use perf tools. You build your application, and then you use this thing called pat build to build an instrumented program. So you can say pat build minus o APA, give it an MV executable, and then it'll create a program like this called executable name plus pat, and then you run that, and that will produce you an XF file which you can run through pat report and get you more detailed information output like we saw in the other one. And you can look at things like hardware metrics from there. And then you can also tell it to do loop statistics with the Cray compiler, and so it can start giving you things like hardware cache misses, and so actually this is output from Archer, not ARCHER2, so there's some Intel stuff in here, but it can start to give you sort of vectorization calls and cache bandwidth and cache misses, and some more in-depth profile in here. And we can get access to these hardware performance counters through here. You can have a look at what performance counters are available for the processor we're running here. If you actually type pat help on the command line, and then you can go through counters and roam and groups, and that will tell you what performance counters are available, and you can specify that when you run your job. And you can also actually have a look here at a file which includes the performance counters down here. But these are the basic ones we get from the AMD Rome processor at the moment on ARCHER2. Summary of TLB activity, summary of bank activity, and then memory bandwidth, load stores, and floating point operations. And we can see, if we look at those in more depth, we can have a look at the L2, L3, L1 data and instruction cache misses and those kind of things. If you're looking beyond this at sort of parallel profiling and look at profiling across applications, then CrayPat generally averages values across all your ranks in your jobs, across all your MPI processes. This doesn't always necessarily make sense, so you may be able to, you can tell CrayPat to not do this kind of processing, or only look at a certain number of ranks, or give you individual ranks data out as well. And likewise for OpenMP profiling, there's some more fine-grained profiling that can be done, where we can show per thread rather than per process, and you can insert CrayPat particular OpenMP profiling function calls in there as well, and it can look at things like load balance across threads and these kind of things. So there's some quite nice features in there, and CrayPat will also tell you how much memory each process is using. And actually, I need to update these numbers because they're wrong, but work out the number of cores you can run on, and more processes using memory. In a parallel application, it is one process using more memory than the other, so you can get out heap and statistics from CrayPat as well. So profiling is the next important thing for us to do. What we'll do with profiling is take an application and try and profile it on ARCHER2 to see if we can see the performance hotspots, and then that would be a way of guiding our optimization effort once we know how to do that optimization. Any questions about that? Whilst I wait for your questions, I'll fix these slides so we don't mention Archer hardware. Now, it's a good question. So how would you interface this with CMake? Do you mean how would you get CMake to produce you build? Yeah, I understand the build environment, because in CMake generally you have debug and you have release versions of your application of your CMake build, and so in debug you have different different compiler flags which are passed, and in release you have different compiler flags. What you would need to do is create a CMake target profiling, and be able to set the profiling flags in that CMake target. Yes, so I think there are CMake targets that you can have a look. I'll just have a quick look at what they are. So CMake target profile. You could definitely, oh yes, okay. So you could definitely replace the compiler call with a build call, but my preference would be to have a separate compiler for the profiling setup, and CMake should let you do that. I'm just having a look at the best way of doing that in CMake, because generally you set your you can set your compilers and your flags for the different sort of release types you're using inside CMake. So let me get back to you on that. It's not what I thought about, but I'm pretty sure it should be reasonably easy to do within CMake. Drop me an email so I don't forget as well, please. Yes, so there are other profilers which are quite nice. So we haven't gone through a list of them here, but the Vampire tools are good for parallel profiling. They're not vendor specific. ARM have what used to be a linear, the map profiler. Generally, you have to pay for that, but that can be quite a nice one if it's available on the system. To get the hardware specific stuff, there's a set of, well, there's the perf tool. Actually, if you're on Linux, the perf tool is a great profiler. If you're on Linux and it's installed, or you can install it, that's got a great set of tools for profiling. Not really for parallel profiling, but for single application profiling, it does a very good job. And then you can get access to things like PAPI, which is an interface to programming, performance counters. There are a bunch of compiler things from Liquid, which is a set of performance tools from German university, which are quite nice. And then each of the hardware vendors will generally do something. So Intel VTune is quite nice. I'm not sure if you have to pay for it anymore or not, because they're starting to release some stuff for free. AMD have a tool which is called, let me have a look. I do have this listed somewhere. UPROF. So AMD have a tool which I think is freely available if you're running on AMD processors, called UPROF. So I think between those you can probably do something quite nice for any given application you have. So as I said, there's the map one as well. There's Vampire for more for parallel profiling. But across those, there should be something quite nice you can get. I think Intel probably have another set of things that you could use as well. Any other questions? If not, and predictably we're slightly late, so apologies for that. Apologies for eating into your lunch break. What we'll do is come back in an hour's time, so 2:15, if that's okay with everybody. And there's a profiling practical to move on to next. So there's a separate profiling sheet, and I'm trying to use Cray on the Cray system to come back to. And if you haven't quite finished the first practical, that's fine. You can continue on that one. But back at 2:15. So all of this is being recorded, and the recordings will be put up online. The actual PDF for the exercises you already have, and you already have the exercise handouts, so that should all work for you if you can't make it this afternoon. But the lecture slides and the recordings are all in the repository. If you can't find them, then send me an email and I can let you know where they are. So unfortunately, we're not getting RDDT onto ARCHER2. There are some other, so DDT is a debugger rather than a profiler, but very useful debugger. There are some other debugging tools which have come on, which we have instead on ARCHER2. So let me just remind myself what they are. But there are other ones which are meant to be equivalent, not equivalent, but there are other ones which are to be used instead. So, okay, yeah. So this here, let me put it in the call. Shows the debuggers we're going to have. Basically, there's a GDB for HPC and then Valgrind for HPC, STAT and ATP are all the tools we can use. Now, unfortunately, I know they're not quite the same as DDT, and they're not quite as graphical and nice as DDT is. But no, we're not getting DDT for ARCHER2, unfortunately. Well, thanks for the question. Luca, it's a very interesting question. In general, a cache miss is always going to slow down the execution. It's not going to overlap with computation. And that's just because the overlap we can only really do if the cache miss was quick enough that you know, the number of registers we have to schedule other instructions would make up for that loss. So we could run something else. We could run enough things in the processor pipeline to make up for the time. Now, if we can remember, on AMD, on this processor we're using here, the cache miss is about 230, 240 cycles. But generally, we've got a pipeline of depth 19, and we only have about 100 registers. So we're never going to be able to run enough things to hide that cache miss cost. So if you're seeing cache misses, you know, significant cache misses on your profile, then it's likely that is going to be impacting your performance, and they're not overlapping. The challenge is to know what is a significant cache miss, because you'll get a profile out and you'll say, you know, 5.4% cache misses, and is that a lot or not? And that sort of changes between processor to processor. But generally, if you're seeing something like, you know, 5% or more cache misses, then it's going to be hitting your performance. And, you know, 2 or 3% cache misses, well, there's nothing you can do about it, because you're always going to get some cache misses. But it's sort of looking at that kind of level of performance. It depends a little bit on the application you've got on the hardware you're running on. So you need to go into a little bit more depth on that. But we'll discuss a bit more about that tomorrow. Well, thanks everybody for the questions. We'll see you back again at 2:15.